Hello everyone, Mr. Bine here. We've now learned in History of the Atom, parts 1 and 2, that most of the matter in the universe is made up of atoms. However, this simple fact does not explain to us why certain materials act in certain ways. We need to have a more complex understanding of matter, because matter is made of many atoms more often than not, and sometimes those atoms aren't the same as each other, and sometimes still those atoms are interacting with each other in particular ways that give matter its properties. So next time you walk up to some matter and you wonder, what's the matter and why does it act like that, hopefully this talk will help you be able to answer that question in more detail. So far we know that if something has matter, then it must be made of atoms. There are two basic categories for all matter: those that are made of the same type of atom, one type of atom, or those that are not. So if all of the atoms inside a chunk of matter are of a single type, then we can call that matter an element. If it contains atoms of different types, then we call that a compound. But there are many different substances with different kinds of properties in this world, such as sodium chloride or table salt, or neon gas, or oxygen gas, or nitrogen gas, or how about some of these lovely substances right here: carbon dioxide, which we breathe out, water, which we drink in, or glucose, which we eat. All of these substances fall into further categories, such as atomic elements, molecular elements, ions, ionic compounds, and molecules. What do these words mean, and which of these substances belong to which category? In order to answer this question, we need to look at how the atoms inside these materials interact with each other. You will recall that atoms have subatomic particles, that is, particles that make them up, including protons and neutrons inside the nucleus of an atom, as well as electrons that run around the outside of that atom, like I'm highlighting in this carbon atom right here. And the number of these particles determines which element an atom belongs to, and in this periodic table of the elements you can see drawings of many different elements. You'll also remember that Dmitri Mendeleev designed this periodic table, or at least the first draft of it, to represent both the atoms' sizes and their chemical properties. Today we're going to talk about that chemical properties piece, because the number of particles inside each of these atoms determines how much atoms want to hang out with each other and bond with each other or not. When two atoms are side by side, the first parts of the atoms that touch are the electrons that are in the outermost ring. So on this hydrogen atom, that means the electron that's going, this little electron right there. That electron, when this hydrogen atom approaches another atom, is going to bump into, say, the outermost shell of electrons on this nitrogen atom right here. And so when these two atoms approach each other, it's these outer electrons that will interact. And depending on the number of electrons, they interact in different ways. So for example, while carbon is very eager to interact with many atoms because of its number of electrons, neon right here is an antisocial atom and will almost never interact with another kind of atom. Why is that? Well, like anything in the universe, atoms seek to become more stable. If you picture putting a glass of water right on the edge of a coffee table, you have a perfect visual for something that's unstable. At any moment, with a slight change in the environment, that glass of ice water might go tipping off the side of the table, fall down on the ground, crash and spill everywhere. Well, the same thing is true of many atoms. Atoms are less stable if their outer shell of electrons is not full. What's full, you might say? Well, the place to look is in this column of the periodic table, the noble gases, because the noble gases don't react with any other substance. They never make bonds. In other words, they are some of the most stable substances around. So their outer shells must be full already. For helium, which has only one shell's worth of electrons, that shell is full with just 2 electrons. So the first shell of electrons in any atom can only fit up to 2 electrons, and once it does, it is full. You can see that full shell of electrons in all the atoms that are larger than helium, like even in this lithium atom, there are 2 electrons. In this beryllium atom, there are 2 electrons. So for all of the atoms in this second period, the first shell has already been filled. However, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine are not stable atoms because they have a second outer shell. So they're not stable yet. Only neon is stable with an outer shell full of 1, 2, 3, 4, 5, 6, 7, 8 electrons, as is argon, which also has 1, 2, 3, 4, 5, 6, 7, 8 electrons in the third shell. So the first shell can fit up to 2 electrons, the second shell up to 8, the third also up to 8. And until atoms have that full set of electrons, they're not stable. They're like the glass of water sitting on the edge of the table. Well, how do the atoms become more stable? They do so by bonding with each other. When they bond, they share electrons, and that helps them fill their outer shells, and once their outer shells are full, then they're stable as any of the noble gases are. Here's an example of what this looks like. You've got 3 atoms over here on the left, which you can tell since there are 8 protons in this atom that this must be an oxygen atom, and you can tell because these only have 1 proton in their nucleus that they must be 2 hydrogen atoms. All of these atoms are unstable. You can see hydrogen is just killing for another electron in its first shell, which needs 2 electrons, and this oxygen atom is killing for 1, 2 more electrons inside its outer shell to fill it so that it has 8 in its outer shell. If all of these 3 atoms hang out, then they can satisfy their need for electrons and become more stable. So here the atoms have combined and started to share electrons. You can see the hydrogen shared one of its electrons with the oxygen, and the oxygen shared one of its electrons with the hydrogen, and same over here. And now the hydrogen has 2 electrons in its outer shell, so it's stable. And the oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell, so it's stable. And this hydrogen atom as well has 2 electrons in its outer shell, so it's stable. So if all of the atoms hang out with each other and share electrons, then they're stable. This arrangement of many atoms all at once sharing electrons is called a molecule. And so this is a molecule of water right here. And molecules are held together when atoms share electrons. Atoms sharing electrons has a special name. We call that a covalent bond. So inside a molecule, when atoms are sharing electrons, they're joined by covalent bonds. Now, there are many ways for chemists to draw covalent bonds. Here's the one that we were just looking at, where it shows the actual atoms sharing the appropriate number of electrons, but drawing something out like that often takes a while. So the most common way that we will draw and represent covalent bonds in this class is just by drawing a line. If 2 atoms are sharing 1 electron, like this hydrogen gave 1 electron to the other one, and this hydrogen gave 1 electron to the other one, then we represent that with a single bond, that is one line that goes between the 2 letters. If, as in the case of these oxygens, this oxygen is sharing 2 electrons with the other oxygen, this one's sharing 2 electrons with the other oxygen, that means we've got a double bond going on, boom, boom, which is represented by 2 lines. So each line between 2 atoms in this structural formula represents the sharing of 2 electrons between those atoms. In the textbook and throughout the class, you might also sometimes see atoms that look like they've been smushed together in a diagram. That's also representing a covalent bond. So just know that when you see that, we're talking about a molecule and we're talking about covalent bonds. Unfortunately, most atoms didn't go to kindergarten and didn't learn that sharing is caring. So from time to time there are atoms that steal electrons from other atoms. And it's not just any atoms either. It's these ones. Fluorine and chlorine. These atoms are super greedy And of course they would be, because all they need to fill their outer shells is just one more electron right here or one more electron right here. So they are greedy as can be to try to get a new electron and become stable, like a noble gas. There are also some really generous atoms that live on this side of the periodic table, such as lithium and sodium, that have one electron in their outer shell, which they are so eager to give up. Because if a lithium were to give up that electron, then it would be left with a full outer shell of 2 electrons. That's the shell that's right underneath. So when fluorine or chlorine gets together with lithium or sodium, something new happens. An electron gets stolen by the chlorine atom from the sodium atom. And so here you can see in the diagram is a transfer of that electron. The electron's up and leaving the sodium atom until it comes and hangs out at the chlorine atom. Now, once you have a chlorine atom with an extra electron, it's no longer called an atom because it's out of balance. It has an overall negative charge, and whenever a particle has an overall charge because the electrons are not equal to the number of protons, it is called an ion. So right now here's what was once a chlorine atom that now got turned into a chloride ion. Same with this sodium. Now that it lost one of its electrons, it has an overall positive charge. It's lost a negative charge, so it's become positive. So that sodium atom has now become a sodium ion. Now these two ions have opposite charges, negative and negative and positive are really attracted to each other. And so these ions will hang out, one chlorine atom, one sodium atom, one chlorine atom, one sodium atom, chlorine, sodium, until it makes this really big crystal. And this isn't just any crystal, by the way. This is what a grain of table salt looks like if you zoom in on it many, many times. So in salts, also sometimes called ionic compounds, there are ions, not atoms. Those are particles that have stolen electrons or lost electrons, and because they have done so, they've gotten charges, they've become ions, and those ions are attracted to each other. The attraction is called an ionic bond. So in salts, the no longer atoms, now ions, are held together by ionic bonds. So next time you shake a little table salt onto your food, realizing you're shaking a salt, that means a long line of sodium ions and chloride ions that are attracted to each other because they have opposite charges, all stacked up inside that salt crystal. And they're held together not because they're sharing electrons, but because the fluorine, chlorine, and bromine ions have stolen electrons from the others, become negatively charged, leaving a bunch of positively charged particles that are attracted to them. To conclude, what's the matter? Well, matter is always made of atoms. If that matter contains just one type of atom, then it's called an element. If the atoms inside that element are covalently bonded together, then it's known as a molecular element. That is, molecules containing just one element, like O2 or N2. If the atoms are not bonded together because they're already stable, then they form an atomic element, such as this neon atom, which has no need to bond to anything since it's a noble gas. What if the matter does contain more than one type of atom? Well, then it's called a compound, and depending on how the atoms are bonded together, they get different names. So, if the atoms are sharing electrons, then they are attached by covalent bonds, and they form a molecule. Examples of molecules include CO2, carbon dioxide, H2O, water, or C6H12O6, glucose. If they don't share electrons, then instead they have gained or lost electrons and are now called ions, meaning that they have a positive or negative charge. These positive or negative particles are attracted to each other and form ionic bonds, and they do so to form a salt or an ionic compound, such as sodium chloride, which is table salt. So next time you're wondering what some matter is, use this flowchart to help you, and you should be all set.